Thank you for click on this video. I, sajal.sasmal, welcome you to complete lecture series of solar photovoltaics. Please click on description for playlist of complete solar cell tutorial. Let's start. Atmospheric effects have several impacts on the solar radiation at the Earth's surface. The major effects for photovoltaic applications are a reduction in the power of the solar radiation due to absorption, scattering and reflection in the atmosphere, a change in the spectral content of the solar radiation due to greater absorption or scattering of some wavelengths, the introduction of a diffuse or indirect component into the solar radiation, and local variations in the atmosphere, such as water vapor, clouds and pollution, which have additional effects on the incident power, spectrum and directionality. These effects are summarized in the figure below. Typical clear sky absorption and scattering of incident sunlight. Absorption in the atmosphere. As solar radiation passes through the atmosphere, gases, dust and aerosols absorb the incident photons. Specific gases, notably ozone, O3, carbon dioxide, CO2, and water vapor, H2O, have very high absorption of photons that have energies close to the bond energies of these atmospheric gases. This absorption yields deep troughs in the spectral radiation curve. For example, much of the far infrared light above 2 micrometers is absorbed by water vapor and carbon dioxide. Similarly, most of the ultraviolet light below 0.3 micrometers is absorbed by ozone, but not enough to completely prevent sunburn. While the absorption by specific gases in the atmosphere change the spectral content of the terrestrial solar radiation, they have a relatively minor impact on the overall power. Instead, the major factor reducing the power from solar radiation is the absorption and scattering of light due to air molecules and dust. This absorption process does not produce the deep troughs in the spectral irradiance, but rather causes a power reduction dependent on the path length through the atmosphere. When the sun is overhead, the absorption due to these atmospheric elements causes a relatively uniform reduction across the visible spectrum, so the incident light appears white. However, for longer path lengths, higher energy, lower wavelength light is more effectively absorbed and scattered. Hence in the morning and evening the sun appears much redder and has a lower intensity than in the middle of the day. A comparison of solar radiation outside the Earth's atmosphere with the amount of solar radiation reaching the Earth itself. The human eye has evolved to the point where sensitivity is greatest at the most intense wavelengths. The standard spectra given above and described in more detail in the appendices give a typical spectra for a sunlight. Computers' models allow for more detailed models of the solar spectra for a particular location and time of day. The simple model of the atmospheric radiative transfer of sunshine, or SMARTS, is used to generate the standard solar spectra. The solar spectrum calculator at PV Lighthouse also gives the solar spectrum as a function of location and time of the day. It uses a slightly simpler algorithm from bird. Direct and diffuse radiation due to scattering of incident light. Light is absorbed as it passes through the atmosphere and at the same time it is subject to scattering. One of the mechanisms for light scattering in the atmosphere is known as Rayleigh scattering, which is caused by molecules in the atmosphere. Rayleigh scattering is particularly effective for short wavelength light, that is blue light. In addition to Rayleigh scattering, aerosols and dust particles contribute to the scattering of incident light known as ME scattering. Scattered light is undirected, and so it appears to be coming from any region of the sky. This light is called diffuse light. Since diffuse light is primarily blue light, the light that comes from regions of the sky other than where the sun is, appears blue. In the absence of scattering in the atmosphere, the sky would appear black, and the sun would appear as a disk light source. On a clear day, about 10% of the total incident solar radiation is diffuse. Effect of clouds and other local variations in the atmosphere. The final effect of the atmosphere on incident solar radiation is due to local variations in the atmosphere. Depending on the type of cloud cover, the incident power is severely reduced. An example of heavy cloud cover is shown below. Relative output current from a photovoltaic array on a sunny and a cloudy winter's day in Melbourne with an array tilt angle of 60 degrees. Thank you for watching the video. Please like and share this video. I will be so happy if you subscribe my YouTube channel. Click on description for playlist of complete solar cell tutorial.